Today we are going to shift gears yet again. So we've been talking about optics, and we're going to stay in optics, but up to this point it's been geometrical optics, where we've been studying the ray nature of light. Now we're going to shift to talk about wave optics, the wave nature of light. That is, light is a wave. And I'm going to actually start out with some demonstrations here. We probably won't even get to the theory on these demonstrations today, but it's a good starting point for our discussion about the wave nature of light. So grab one of these glasses and pass them down. I do want these back. Please don't write on them, basic standard things. Wait. I did that in the opposite order. Keeping one, not giving one. So take one, pass them down, put them on. I haven't passed these out before this class, have I? Y'all remember? No. Okay, good. So, wait for them to get back there.
No, it's right.
Okay, so we all have glasses. She said that.
Oh.
These do something cool. What they're not doing is they're not just focusing light. But if you look at things like, if I look at Abby, and then I look above her, I see another image of Abigail. But in that image above Abigail, I see some weirdness. I see first an Abigail that is blue, and then above that I see a kind of like rainbow version, and then I see a red one on top. You guys see that kind of thing? Or if you look at the lights, instead of looking directly at one, look at one that's across the classroom from you. It gets more of an effect. You should see that those lights are different colors. What specific colors do you see when you look at the lights? You look at, of course, not directly at them, but the images off to the side. Okay? There is a very clear, I'm saying you're trying to focus on them, there's a violet and then a bluish, greenish blue, and then a green, a very faint yellow after that green. Actually, that might be an overlap. And then a red. You see all those? Well, these glasses are doing something weird to make it so we can see that. And that weirdness has to do with the wave nature of light, what we're going to start understanding with today's lecture. Now I'm going to do a couple more demonstrations here. First, I'm going to turn off all the classroom lights. So it's kind of dark. I have to turn off the projector light to get it even darker here. And now I'm going to turn on a little light here. So right now the light is quote on with 0 voltage going to it, so nothing. Raise that voltage just a little till we see something. Now if you look at the filament, what color is the filament? It's orange. And if you look off to the side, do you see colors? No, you should. You should see colors at an angle that's, if you hold your arm out about the width of your hand away from the center. You should see what looks kind of like a rainbow. It's very faint. And what color is closest, what color is farther in that rainbow? A rainbow that's going to be off to the side. Okay, there are vertical ones as well. That's because these glasses are made for little kids to wear at parties. And so they do the effect in 2 directions instead of just one. So focus on the horizontal ones. So if you look out to the side of the horizontal ones, you should see some colors. Well, I'm gonna heat it up to make it more clear, because it turns out that we have a couple laws about this that people got from studying just what you're looking at. And one of them, Stefan's law, says that the amount of radiation emitted, because this is one of our three types of heat, radiation, the amount of radiation emitted is proportional to temperature raised to the fourth power. So if I double the temperature, 2 raised to the fourth power is 16. Doubling the temperature gives off 16 times more radiation. So I will raise it. Now the color has changed, right? It's not nearly as orange. It's closer to white. And now you should very clearly see what looks like rainbows off to the side. And what is the color closest to the light bulb? Blue. And what's the color farthest from the light bulb? Red. Okay, so we have that spectrum of color. Those colors you see off to the side are the actual pure colors that exist. So that's showing the spectrum of pure colors. Any color that you recognize that's not one of those is because it's a composite. It's combining different colors together. Now, if I make it hotter, notice both what happens to the color here and what happens to the spectrum. So if I make it hotter, what happened to the color of the filament? Okay, it became brighter and its color became more white. What happened to the rainbow to the side? What happened to the spectrum? It got brighter, and what happened to the edges specifically? Stronger in which color?
Blue.
Blue. Yeah, there's a lot more blue. The red was always there. The red was always there. The blue wasn't. And so when we get it really hot, we say it's white. And when it's white, we have a broad spectrum of the visible colors, all reasonably strong. That's what we perceive as white. Remember that our eyes have only 3 types of color sensing elements, 3 types of cones. The one that we call the red, the one we call the green, the one we call the blue. If we have equal amounts of activation of each of those types of cones, that's what our brain calls white. So you can see the different colors that correspond to temperature by using these. Now that's all fine and good. I think it's fun. Now let's shift over to some gas tubes. So here is a hydrogen gas tube. And so this has hydrogen gas. Hydrogen gas that I can see has a lot of impurities in there. How do I know it has impurities? Because if it was pure hydrogen gas, when you looked off to the sides, you would only see like 5 distinct lines. You know, see how there's like a faint rainbow all the way across? That's because there's a lot of water that's gotten into this tube. I was worried about that because the edge of the tube, the cap, like looked like it was wiggling, which means the air probably got in, and definitely it has. So it's not a very good example. Let's change. Here's a helium tube. Let's see if this helium tube is in better shape. Yeah, that's definitely better. Now you see very distinct lines. Those distinct lines are really important for our understanding of the energy states of an atom. And so we'll study those later. When we get past optics, we'll come back to this information. Looking at those lines, determining what their wavelengths are, is very important to both our current understanding and the historical development of our understanding of atoms. But these glasses allow us to see each of the colors that make up that center line distinctly. So you can see that peach-colored center line is actually made up of a couple blues, a couple greens, a very strong yellow, a couple reds. So it's mixing all those colors together that gives us what looks like the peach color. We're going to study today the optics that allows these glasses to do that. Like I said, we probably won't get specifically to these glasses, but we'll understand the effects. This is, by the way, called diffraction, which is the bending of light around an obstacle. I'm turning on the lights now just so you don't go, ah! Yeah. All right, so any questions about this before I dive in? Anything that has piqued your curiosity that you want to talk about right now? No, I want them back.
What are we doing?
No.
Oh,
Carson's like, but I already have 5 in my backpack. Not true. He's joking. All right. First thing we have to understand is constructive and destructive interference. Now, we've actually talked about this already when we talked about sound waves. We talked about constructive and destructive interference. If I have 2 waves, there's one wave, there's another wave, and they're in the same location. When we had a wave on a string, it was easy to understand. A sound wave, a little bit easy to understand. An electromagnetic wave, a little harder to understand. But what happens is, if they're the same location, they do what we call superimpose or superpose. Superimpose and superpose mean exactly the same thing. And their amplitudes add up. So the displacement at any point is equal to displacement 1 plus displacement 2, which means that if they're in phase like this, in phase, it's a term I just use automatically. We haven't talked about it today. We may have talked about it a long time ago, but it's really important that we understand what in phase means. In phase. Does anybody have a feeling on that?
They're going together.
Okay, they're going together. In phase means that the time when one has a peak, the other one has a peak. So they're in phase if at the same point they have peaks, the same point and the same time. So if I have light like this that's in phase, then I will have amplitude is equal to amplitude 1 plus amplitude 2, and we call that constructive. Constructive interference. So if I have light waves that are in phase, that is, their peaks are at the same time at the same location, their minima are at the same time at the same location, so they're just going like this, then the total displacement is just going to be adding the 2 up. Total amplitude then will be the sum of the 2. That's if they're in phase. What if they are, quote, out of phase? What would that mean? By contrasting to in phase, what would out of phase mean? That's right. The peaks and troughs correspond rather than peak with peak. And in that case, we're still going to have the displacements are adding together, but because they're exactly out of phase, when one's a positive D, the other one's a negative D. And so it turns out the amplitude is going to be amplitude 1 minus amplitude 2. Actually, you better put an absolute value sign because you can't get a negative amplitude. So that's what we call destructive interference. If it's destructive interference, okay, so I got to add the word destructive interference up here. If it's destructive interference, your amplitude goes down. If they had exactly the same amplitude, if I had 2 identical waves but they were out of phase, what's the total amplitude when I add the 2 together? 0. So they would completely destroy each other if they were identical waves but they were out of phase. If they were in phase and identical waves, what would happen to the amplitude? It would be twice as big, and we call that constructive. So that constructive and destructive interference is very important. That's what these glasses were utilizing, was destructive and constructive interference. Now there's another word, it's actually the first word here that's highlighted, incoherent. let us suppose that you deemed my lectures incoherent. What would that mean? Okay, we had contradictory to each other. Something else?
Unable to be understood.
Unable to be understood.
Fragmented.
The what?
Fragmented.
Fragmented. Those are all good definitions of incoherent. Incoherent, when we talk about a wave, means basically the same thing. There is the fragmented that Alex used is the one that I'm going to latch onto because it's the one that is the most directly applicable. They all mean the same. It's incomprehensible. It's fragmented. If I have an incoherent light source, that means that I don't have a fixed relationship between the phase of light. That is, I can have light that's coming out at one place, the light is coming out like this, and another place is coming out like, well, I'm going to make them at least the same wavelength. Another place is coming out like this, and another place is coming out like this. There's no set relationship between them. They're just kind of random. Furthermore, I might have it suddenly shift. So the phases could shift. That would also be a hallmark of incoherent light. So incoherent means that the phase, okay, we talk about in phase and out of phase. The phase is basically the pattern of peaks and valleys, peaks and valleys. If it's incoherent, that pattern is just random. If it's coherent, it's very nice and repeatable. No matter where you are, it's going to be the same, all working together, so to speak, all organized. Why is that a big deal? Because when we talk about the wave behavior of light, coherent light is easy to understand the wave behavior of. Incoherent, very different situation. So here's a picture to try to illustrate. This is perfectly coherent here. All of the light waves are doing the same thing at the same time at the same place. The picture on the left, you notice there is a pattern here. So there is a fixed phase relationship, but it's not all peaking at the same time. So when we talk about coherent, if there is a fixed phase relationship, we'll say that's coherent. Not necessarily in phase. This is not in phase. Because there's a different time when each one's at a peak, but it's coherent because you have a fixed phase relationship. So how does that work out? First, we should recognize all real waves fall somewhere between the extremes. All real waves have some range in which you have coherence, but then it changes. If I have a laser, you guys are probably too young to think about that. If I have a laser like this, it has what we call a wave train, a distance of coherence. And the average wave train for a laser like this, is measured in kilometers. That means that light has to travel like a kilometer before it will change from this to an abrupt shift. And so it's highly coherent. Lasers are good sources of coherent light. Should we have enough time in class this semester to talk about, we'll talk about what makes lasers, light amplification through stimulated emission of radiation, what makes them coherent and what makes them cool. But that's a really good example of a coherent light source. A traditional light bulb, an incandescent light bulb, which is what this thing here is, that's pretty much incoherent. The light comes off with wave trains that are really short, and then it starts over at some random part of the phase. So you don't have a strong phase relationship with that. Yet we did see that our glasses worked with that, because it has a very short wave train, but it does have some coherence. So all real waves fall somewhere between completely coherent and incoherent, and it was enough coherence for our glasses to work with that. And I'm going to jump straight to how we do some calculations with this. So we're going to talk about the Michelson interferometer. What's the point of this Michelson interferometer? Well, first of all, interferometer. This is a device for looking at the interference between light waves. Michelson developed this. I believe this was part of his study trying to identify properties of the ether. I haven't talked about the ether in class, have I? There's a really good reason why. We don't believe in the luminous ether. That was a scientific theory that, based on Michelson's work, was debunked. It was a theory that said that light, because light is a wave, it must have a medium. It must have something that supports the wave, which makes perfect sense. Sound. Sound waves have to have a medium. The sound you're hearing right now is going through air. That's the medium for the sound. If there was no air between you and me, I could do whatever I wanted. You wouldn't hear anything because you don't have anything to vibrate in your ears. Right? It has to have a medium. And so they thought light must be the same. There must be some medium. One of the first things they tested was, let's see if light goes through a vacuum. So you take a bell jar and you pump as much of the air out as you can. No problem, light goes through. And so the scientists said, okay, so clearly air is not the medium for light, it's something else. And that's where they came up with this luminous ether, or luminiferous ether, whatever it's called. And so they figured it must be like air for sound waves. So if I have something traveling the sound wave, like if I am traveling, or let's say I'm standing here and there's a wind blowing this direction, and I yell, who's going to hear me first? A student that's 100 yards on that side or 100 yards on that side if the air is traveling like that? Right, because the speed of sound is a speed with respect to the medium. And so if the medium is moving, the speed going in the direction that it's moving is going to be faster because it's going to be the speed of the medium plus the speed of sound of the medium. And so Michelson said, let's do something like that to measure the speed of light in different directions. And then we'll see, okay, so it's sitting stationary in the lab. Is the medium moving in the lab? And then we'll go and we'll do something like put it on a railroad car that is traveling very smoothly at constant speed and see now, can we measure the difference in the speeds? Well, his experiments all showed a null result. That is, they showed no difference in the ether regardless of the speed of his test. If you're a flat earther, that's just further proof that the earth is not moving somehow. They bring that up. Of course, these people don't know their science. I saw somebody talking about the Michael experiment. The Michael experiment? Yeah. Actually, I think it might be called the Michael Moore experiment because it's the Michelson-Morley experiment. Anyway, that's really the purpose of this originally. But what it is something that we can understand and work with. You use a light source. Notice this shows a laser beam. Why a laser beam? What's special about a laser that we just talked about? It's coherent. So it's that's why I have this pin, because it's. So we have a coherent light source. Now that light comes and it hits a beam splitter. S stands for splitter. So it splits the beam 50-50. Half of the beam goes this direction, and half the beam just goes right on through. Then each one hits a mirror, so M1 and M2. Okay, I guess I cut off M2. M1 and M2 are the mirrors that reflect the light back. They hit the beam splitter again. The beam splitter again is going to do a 50-50. So I'm going to have some light that gets dumped back that way that I just don't observe. But then I have a lot of light that goes this way. Those two beams then came back together. So I started with two beams that were perfectly coherent, perfectly in phase. They go down two different paths, they come back, and then they join up together. And we look to see how the two beams are going to add together. Are they going to give us constructive interference or destructive interference? Now, to get perfectly the same path lengths for those two is impossible. We don't even try to. What we're going to do simply is say, now let's move one of these mirrors and measure how much the phase changes when I move it. Because we can't ever get it exactly the same. For Michelson-Morley experiment, they actually rotated the device 90 degrees to see how the speed of air was in each direction. Now that we're not doing the Michelson-Morley experiment, we're going to do a specific case of this to see how it's useful. So I have a problem to see how this works out. So I did this problem this morning when I woke up. I was probably more awake then than I am now. Suppose a transparent vessel with a cavity 30 centimeters long is placed in one of the arms. So what that means is I'm going to put in here a little cuvette. Okay, my artistry is lacking. But I put a little cuvette that the light goes through. Now let's start with a real easy question. How many times is the light going to go through that cuvette? Twice. I have to keep that in mind for my analysis. It says that it has a width. Of 30.0 centimeters. So the light's actually going to go through it twice, so it's going to have a total light path inside of that that's 60 centimeters. Okay, getting back to the problem. So we have that transparent vessel in there. The vessel initially contains air at 0 degrees Celsius and 1 atmosphere. So it's just air. Now we connect a vacuum pump and we pump out the air. If you pump out the air, what's different for the light path?
It'll be a vacuum, so it would have a fraction. That's what it's called.
No, but we're in the ballpark of why. The index of refraction, the speed of light, right? Speed of light is c over index refraction, or whatever. The index of refraction is c divided by the speed of light in my material. The speed of light in vacuum is different than the speed of light in air. And so the speed of light will have changed in this little cuvette. And so the number of wavelengths of light that fits in that cuvette changes when I pump out the air. And so what we're going to do is say, how many wavelength difference did I have? Well, it tells me here that it went through 274 bright fringes. That is, I started, let's say I'm looking at the intensity at the center of this plate. And I started with the intensity as bright. And then as I sucked out the air, so I have the intensity here, and I'll have time here. And so before I started sucking out the air, it was just constant. And then when I start sucking out the air, it goes. So here's when I started evacuating. And it keeps oscillating until when I get to the end, it goes. It stays up here. So this would be completely evacuated, which you should know is not possible. It will asymptotically approach that. And so counting the peaks, we have 1, 2, ... And we get to 273, 274. So as we pumped out the air, the number of times that it reached maximum intensity, that is where it reached constructive interference, was 274 times. Now this is an actual doable experiment. And the question then is, if I was using a laser with a wavelength in vacuum of 633 nanometers, what's the index refraction in that air? I throw this to you as intelligent and wise students. How does the index refraction, i.e. the speed of light, relate to the number of fringes I saw there? Let me take you piece by piece. What does it mean for my intensity to go from a peak to 0 and back to a peak when I'm looking at the interference between the two light paths? I had the number of wavelengths difference between where the beams were split and where they came back together was 1 wavelength different for each time. So that means my number of wavelengths shifted by a total of 274 in that total path. Now, where's the only place that the wavelength was changing? In that chamber that's 30 centimeters wide. And so what I can say then is that the difference in the number of wavelengths in that chamber was 274. So what I'm going to have to do then is say, well, how many wavelengths fit in the chamber initially? So N initial would be equal to, well, because we had to go through 2 times, I put 2 because we had to go through 2 times, the length of the chamber divided by the wavelength of the light initially. Right, that's how many wavelengths fit in there. And then after I sucked out the air, it's 2L over the wavelength when there's no air. How does the wavelength relate to the index refraction? I'll start with this. F lambda equals V, right? That's a fundamental rule for us. What's happening to the frequency when I change the speed of light? Clicker question we had within the last 2 lectures. Important fundamental concepts. We can't do any problems without these ideas in our head. If we change the speed of light, what happens to the frequency of a light wave? It doesn't change proportionally. It cannot change. Remember my example was talking about a wave on a string. And if I have a string that's 2 strings knotted together, one thicker and one thinner, so you have different speeds, the knot has to stay together on both sides. Otherwise, you've broken it. So the frequency has to be the same on both sides. The wave speed will be different, but the frequency stays the same. So frequency is the same on both sides. So the frequency is constant. And so I will say the frequency is equal to the speed of light in vacuum over the wavelength in vacuum, which is what they gave us here. The vacuum wavelength is 633 nanometers. And then the wavelength is equal to speed of light over frequency. And so wavelength 1 is going to be speed of light 1 over frequency, which would be speed of light 1 divided by c times the wavelength in vacuum. But this term here, speed of light over c, that's 1 over n. So the wavelength 1 is the wavelength in vacuum over n1. Wavelength 2 is wavelength in light over n2. So I can finish out these equations. Didn't give myself enough space. Nobody likes to put divided by. Right? That's kind of ridiculous. Instead, we just put it on top. So the number of wavelengths that fit in my cuvette in index refraction 1, which was air, is 2 times the length of my cuvette over the wavelength in vacuum times n1, the index refraction in air, which is what we're looking for. And in the second case, where it turns out n2 is vacuum, so n2 is just exactly 1. So that's the number of wavelengths that fit in my cuvette in air and in vacuum. And what we have from our data is that the difference in those numbers of wavelengths is this 274 bright fringes. So now I have an equation that says delta n is equal to 2L and 1 over lambda 0 minus 2L and 2 over lambda 0. I'll factor out 2L over lambda 0. And so there's an equation for my delta n and delta little n. Well, now I'm pretty much done. I want to find what n1 is. So let's multiply notice I put 1 without anything else. That is exactly 1. So I need to calculate this wavelength over 2L times 274. So that's going to be 633 nanometers over 2 times 30.0 centimeters times 274. So we get out the calculators. Somebody get out a calculator and tell me this number, please.
So it's -1 after you do the answer?
No, we're doing this calculation.
Oh, 2,897.
Okay, it's,
No, I didn't have it.
yeah, the units is wrong, the number is right. Because, like I said, I did this morning, so I actually know the number.
0.0028907.
Okay, I only have 3 significant digits, so I will round this 1 extra digit, so I'm keeping 1 more than my sig figs there. So what's the index of refraction? I add 1 to that. And notice my answer now has 7 significant digits because the 1 was infinite number of significant digits, and I was good out to the 9 there, which was the 6th decimal point. So using my significant digit rules, my answer is going to be good to the 6th decimal point when I add the 1. So this gives us a very accurate measurement of the index refraction of air at 20 degrees Celsius and atmospheric pressure, which is really cool, right? It's not an ultimately difficult experiment to do. You just have something there to measure the changes between constructive and destructive interference, and then you count them up. So that's a very practical application that shows the wave nature of light. Another example of showing the wave nature of light is thin films. So here is a pretty picture. What you're seeing is we have light that's coming from this side and hitting a film of, for making bubbles, like blow bubbles. And then you have pretty colors. You guys have all seen this, right? Probably didn't marvel about what makes the colors. But now we're going to look at that. What makes the colors is the interference of light from thin films. So here's a picture showing a thin film. Notice we have the index refraction on the incident side, the index refraction in the film, and the index refraction on the transmission side. Light, when it hits an interface from one material to another, is going to reflect. And the reflection coefficient, the value to tell you how much light is reflected, is the ratio of the differences in indices of refraction divided by the total index, the sum of the indices of refraction squared. It turns out for a glass-air interface, that's about 5% of the light is reflected. So this incident ray is going to have about 5% of the incident rays reflected. About 95% goes into, I'm doing it for glass. So 5%, 95%. When it hits the next surface, let's say it's going from glass back into air, what percentage is going to be transmitted? Note that you have the same indices of refraction, hence that same reflection coefficient. So once again, will be 95% transmitted. And so 90% of your light comes out. It's actually 90.25% if you want it correct. And how much is reflected? It's 4.75% of your initial light was reflected back. That hits the next interface. That times 0.95 is 4.51% of your original light comes out in ray 2. And the rest of that 4.75, so 0.24% goes this way and so on. So obviously if that's 0.24%, roughly 0.23% came out on the next one. Well, for the light that went through, you have 90% of your incident light versus a quarter of your incident light, to be, generous. You're not going to see much difference. The interference between those is going to be a very small amount because the second one is so small in intensity compared to the first one. But for the light that is reflected, the difference in 5% and 4.51%, that's not a very big difference. So this is the side where you're going to see big interference effects because the amplitudes are similar. For the transmission, the amplitudes are very different. You don't see much. So now let's look at how we actually get our intensity for the reflected. So actually, I have some rules, but first I have two clicker questions. Clicker question number 1. What happens to a transverse wave when it is transmitted from a slower to a faster wave speed string? Now notice we've already established the frequency stays the same. So we're not asking about the frequency. If the frequency stays the same, clearly the wavelength is going to change. Whoops. I shouldn't have written that down because this is one where you answer multiple questions. Oh, it's not open for you. Not sure. Let's see. Maybe it'll open for you. Maybe it never will. Okay, now it's open for polling. What happens to a transverse wave when it's transmitted from a slower to a faster wave speed string? So answer all that are correct and hit enter. We have 4 people that have answered twice. Okay, we're now up to 8 people who've answered once. It was 4 that answered twice and 5 that answered once. Okay, 4 remaining. 3. I see you trying. Uh-oh. There you go. Okay. There you go, Corsa. All right. We have, I'm going to write down the numbers before I move on because otherwise it will erase them and I'll never know what they are. So there's the, and just to spite me, it stayed there. We had 12 that said the wavelength shortened and 6 that said that it lengthened. How do we know which one's correct? Well, we have what I had written up here. The frequency is constant. So wavelength is equal to the speed over the frequency. And so transverse wave, when it's transferred from slower to faster, so if speed goes up, what has to happen to wavelength? It also has to go up. So these 6 were the correct ones. Because it goes to a faster speed, the wavelength goes up. Now, the frequency, I had written this down. I erased it. Obviously, those 4 people didn't see that I had written it down and said it at the beginning. The frequency cannot change. It's a really important fundamental thing. And then we have this last one. The transmitted wave has a phase inversion. Okay, hot tip. Transmitted wave is never inverted. It's the reflected one that may or may not have a phase inversion. Because I'm out of time, we will continue with this next class period. Actually, we'll continue with this in lab, but that will be our next class period.